Good morning students. I am Dr. Hepsi Pramila Devamani, Assistant Professor of Physics, V.V. Vanya Perumal College for Women, Virudhunagar. Now I am going to explain about the topic Generation of Electrical Oscillations with LC Circuits. We are going to see a circuit which is made up of an inductance L connected parallel to a capacitance C. Let the capacitor be charged by connecting A and B across a battery. The battery is now removed. The capacitor discharges through the inductance. The capacitor gets charged with opposite polarity due to the action of the inductance, which provides path for electrical charges to flow from the one plate to the other plate of the capacitor externally. This one is the circuit in which the inductance L and the capacitance C are connected parallel to each other, and we are going to connect the battery between the 2 points A and B. The inductance makes use of the magnetic energy established around it for this. Again, the capacitor discharges by sending electrical charges in the opposite direction through the inductance and recharges. The process continues indefinitely each time the magnetic energy around the coil and the electrostatic energy in the capacitor getting interchanged. The process by which the voltage VAB across A and B varies sinusoidally is known as electromagnetic oscillation. The frequency of oscillation is given by F is equal to 1 by 2 pi square root of LC. Now this one represents the damped oscillation. In the inductance coil may possess some ohmic resistance, and due to this there is a loss of power in each cycle of oscillations. The result is that the amplitude goes on decreasing at each cycle, that is, the oscillations are damped, and this one is represented in this diagram. In order to get the oscillations with constant amplitude, which is known as the sustained oscillations, the energy loss must be compensated from an external source such as battery. And this diagram shows the sustained oscillation in which the amplitude remains constant. Now we are going to see what is an oscillator. Oscillator is an amplifier with sufficient gain and positive feedback. It gives a periodically varying voltage waveform as its output be not even without any external input. The oscillator actually draws electrical energy for this purpose from the DC power supply connected to the oscillator. This one is the black diagram for oscillator, and waveforms represent the square wave, sine wave and sawtooth wave. The basic elements of a feedback oscillator are shown in the figure. When the oscillator circuit is switched on, random noises, that is, a small voltages of wide range of frequencies, are produced by the resistors or even from the power supply switched on. This is supposed to be equivalent to applying a small noise voltage at the input terminal Y. This is amplified by the inverting amplifier, producing a phase change of 180 degree at the output. This one is the circuit diagram for the oscillator. The first block A represents the amplifier, and part of the output of the amplifier is given to the feedback. The output of the feedback network is again given to the input of the amplifier. The amplified output signal is passed on to the input side through a feedback circuit. The feedback circuit may be an LC or RC network. The feedback circuit has a resonant frequency FC. It allows the signal of this frequency to pass through it. The feedback circuit also produces 180 degree phase shift and permits only a fraction of the output to appear at the input side of the amplifier. The phase shift of the signal around the closed path containing the amplifier and the feedback is 180 plus 180 equal to 360 degree or 0 degree. The amplifier amplifies the signal of frequency FC. It is fed back again and again, and the amplitude of the output B0 goes on increasing. This is a result of initial condition that closed loop gain A beta is greater than 1. This is due to the positive feedback. However, due to the non-linear behavior of the amplifier device, the closed loop gain of the amplifier reduces to 1, and the amplitude of the output remains at the steady value. then we get a sustained electrical oscillations of the output V naught at a fixed frequency F naught. The frequency F naught is defined by the circuit parameters of the feedback path. This principle is summarized and is given as percussion criterion for oscillations. The net phase difference around the feedback loop must be 0. That is, the feedback voltage must be in phase with the input voltage to the amplifier. The closed loop voltage gain A beta of the circuit must be equal to unity. That is, A beta equal to 1. Here A is the gain of the amplifier and beta is the feedback ratio. A equal to 1 by beta. And this graph shows that in the left side A beta is greater than 1, and here we are getting the damped oscillations, and the right side A beta equal to 1, it gives the sustained oscillation. That is, the oscillations are having the constant amplitude. Now we are going to see the essential sections of an oscillator. An amplifier and of sufficient gain with non-linear active device like transistor to fix the amplitude of the oscillations. A network produces oscillations at the desired frequency. This part is known as tank circuit. A feedback circuit to supply a part of the output power to the tank circuit in correct phase to aid the oscillations. That is, it provides positive feedback. A DC power supply. Now we are going to see the Hartley oscillator with transistor. Hartley oscillator is a type of oscillator circuit which generates sinusoidal output signals. That is, the output voltage varies with time as a sine curve. Hartley oscillator circuit using NPN transistor in the common emitter mode is shown in the figure. It is an oscillator. It is an amplifier with a positive feedback arrangement. The transistor amplifier contains RC as the load resistance, RE as the emitter resistance, and CE is the bypass capacitor to provide the AC path. VCC is the power supply to the transistor. The resistance R1 and R2 form the potential divider arrangement. The voltage across R2 gives the necessary base bias to the transistor. The input to the amplifier appears to the base through the capacitor C1. The output is available at the collector through the capacitor C2 with respect to the ground. The value of the components RC and RE are chosen such that the stage gain of the amplifier is greater than unity. That is, A is greater than unity. And this one represents the circuit diagram for Hartley oscillator with the transistor. The feedback circuit is a tank circuit containing the inductances L1 and L2 and a variable capacitance C. L1 and L2 are inductively coupled. That is, any change of flux in L1 occurs at L2 also. Because of earth connections at G, the potential at Q and P are 180 degree out of phase. If Q is positive going, P is negative going in the potential. Working. When the switch is closed, the collector current starts increasing. The potential at the collector BC starts decreasing, making the end Q negative going in potential. Hence, the potential at P is positive going. This makes the transistor to conduct more and more due to positive feedback action. This collector voltage continues to decrease till Vc equal to 0. That is, the transistor is in saturation, conducting the maximum current. Now, the rate of variation dIc by dt equal to 0. With no current in the feedback path, the magnetic field in L1 collapses and discharges through the capacitor. The potential at P and hence that at the base now starts decreasing and the collector current starts decreasing. This causes Vc to increase and the NQ becomes more and more positive and the NP goes more and more negative. This trend goes on till the collector current is 0 and Vc equal to Vcc, that is the maximum value. The transistor is now in cutoff state. Again dIc by dt equal to 0. With no current in the feedback circuit, the magnetic field in L1 collapses in the opposite direction and the whole process repeats. Thus the output goes on decreasing, increasing and again decreasing and so on, producing sinusoidal voltage waves at the output. The coil L2 couples the collector circuit energy back to the tank circuit by means of the mutual inductance between L1 and L2. In this way, energy is continuously supplied to the tank circuit to overcome the energy losses in the tank circuit. The LC tank circuit, which is a feedback path, introduces a phase shift of 180 degree at its resonant frequency, and the transistor in the common emitter mode produces a phase shift of another 180 degree between the input and the output. Thus, the net phase around the loop is equal to 2 pi radian, that is, there is strong positive feedback. As these two conditions are met with, the circuit readily functions as an oscillator and the electrical oscillations are maintained. The frequency of oscillation is given by f is equal to 1 by square root of LC, where L is equal to L1 plus L2 plus 2M. Here M denotes the mutual inductance between the two coils of self-inductance L1 and L2. C is the capacitance in the tank circuit. Sustained oscillations will be produced if HFE is greater than or equal to L2 plus M divided by L1 plus M, where HFE is the forward current gain of the transistor. The oscillator can be set into working by adjusting the value of L1 and L2 initially. The frequency of oscillation can be changed by varying the capacity of the capacitor C in the tank circuit. The Hartley oscillator is easy to tune. It can be used to produce electrical oscillations of a wide range of frequencies. Hartley oscillator is commonly used as high frequency local oscillator in radio receiver and for the production of ultrasonic waves using piezoelectric crystal in the tank circuit. Now we are going to see the conditions for oscillation. For an oscillator to start functioning, the positive feedback must be strong, that is, A beta must be greater than 1, or A is greater than 1 by beta, where A is the open loop gain and beta is the feedback ratio. For a common emitter amplifier circuit used in this oscillator, the voltage gain A is equal to RC divided by RE. RC is the load resistance and RE is the dynamic resistance of the base emitter junction. Now RC divided by RE must be greater than 1 by beta. The feedback ratio beta equal to voltage fed to the base divided by output voltage at the collector, that is VF divided by VO. The output voltage is across L2 and the feedback voltage is across L1. Therefore, beta is equal to I into L1 omega divided by I into L2 omega, where I is the circulating current at any instant in the tank circuit. So, we get beta is equal to L1 by L2. Using this value, we can write RC divided by RE is greater than L2 by L1. In terms of HFE of the transistor, since the gain A is equal to HFE, we get the condition HFE is greater than L2 divided by L1, since A equal to RC divided by RE. This is the condition for oscillation. The phase difference of 180 degree by the feedback network required for the oscillator is available only at the resonant frequency of the network. Hence, this resonant frequency is the oscillator frequency. At resonance, reactance of inductance branch must be equal to reactance of the capacitor branch. So, XL is equal to XC. So, XL is L1 plus L2 plus 2M into omega equal to XC value 1 by C omega. So, omega squared is equal to 1 by L1 plus L2 plus 2M into C. Omega squared is equal to 1 by LC, where L is equal to L1 plus L2 plus 2M. So, omega is equal to 1 by 1 by square root of LC. Already we know omega is equal to 2 pi f. So, 2 pi f is equal to 1 by square root of LC. From this we can get f is equal to 1 by 2 pi square root of LC. So, this gives the frequency of the Hartley oscillator. Thank you.